Hi everyone, in this video I'm going to give you some step-by-step instructions for how to graph polynomial functions. What we're going to start with is just exploring the type of information that we need in order to graph a polynomial function. So say I tell you that the roots of my polynomial are -2, 1, and 4. So these are the numbers which I plug into my polynomial and get out 0. That means that, for example, f of -2 equals 0, so -2 comma 0 is on the graph, 1 comma 0 is on the graph, and 4 comma 0 is on the graph. So the roots tell me the x-intercepts. So I can plot these, -2, 0, 1, 0, and 4, 0. And I need to figure out how to connect up these dots, so I need some more information. I also know that the y-intercept is 0, 4, so I'll go ahead and plot that. Then I know that my graph is increasing from -infinity all the way up until 0. So all the way on this side of the graph until I get to this dotted line, my graph should be going up. I'm decreasing between 0 and 2, so between the dotted lines, my graph should be going down. And then I'm increasing again from 2 to infinity, so afterwards I should be going up. So this tells me how I can connect up these 4 dots. So as I come up to this one, I should be increasing. I'm still increasing until 0. Then I've gotten to the dotted line, so I need to start decreasing at 0. And I'll decrease until I get to the next dotted line. Then I have to increase again. Now, this graph isn't necessarily perfect because there are many ways I could have connected these dots and still satisfied the increasing and decreasing properties. This orange line, for example, is increasing until 0, then decreasing until 2, and then increasing afterwards. So sometimes it helps to find another point. So say we were given that f of 3 equals -3. Then I know that 3, -3 is on my graph. So I go to 3, -3. Now I have an extra point to connect up. So I know that around here, my graph should go through that point, look more like the green line. So the information that's useful is roots, y-intercepts, increasing versus decreasing, especially what's happening as we go toward -infinity and +infinity, and maybe having some extra points. So given an equation, if I just gave you a polynomial like this, how could we get this information? That's what we're going to do next. So in order to find roots, I need to find zeros, or x-intercepts. So the strategy is we take our f of x, set it equal to 0, and then solve for x. So this usually involves factoring. If we find the factors of our polynomial, we'll be able to find the roots. That's just the factor theorem, which you've seen before in section 2.3. To find y-intercepts, I plug 0 in for x and find y. So in other words, do f of 0, and then 0, comma, whatever number I got for f of 0 is my y-intercept. To find the end behavior, so what happens as we go to the left or the right, so we can either have both rising, both falling, one up, one down, or one down, one up. This is the leading coefficient test. And this you saw in section 2.2. So we're using strategies from other sections here, putting it all together. Then finding the shape of the graph. So to find intervals of increase and decrease, you really need calculus. But we don't know calculus yet, so we'll use another strategy called test points. So the best way I can explain this to you is through an example. So say my polynomial is x minus 1 times x plus 4. Then, if I'm trying to graph it, I know that I have a root at 1 and negative 4. But I don't know what happens in between these. So what I can do is I can pick a point in between 1 and negative 4. So let's say we pick 0, because that's an easy one to plug in. And I find f of 0, because that will tell me the y value here, so I know if the graph goes like this, or if it goes like this, or if it does something funny in between. So f of 0 is just going to be 0 minus 1 times 0 plus 4. Sorry, that's hard to read, but that's going to be negative 1 times 4, which is negative 4. So that means f of 0 is negative 4, so I have a point way down here with y value negative 4, and that means that my graph goes this way instead of this way. So let's do a couple of examples where we use these steps to find the graph of a polynomial. So here's the example that I want to start with. My first step is to find the roots. So to find the roots, I need to use factoring or the factor theorem. So what the factor theorem says is if x minus b is a factor, b is a root. So since x minus 1 is a factor, 1 is a root, and x minus negative 2 is the same as x plus 2, so negative 2 is also a root. So now I can plot those. These tell me the x-intercepts are 0, 1, 0, and negative 2, 0. So here's 1, 0, and here's negative 2, 0. Another piece of information I have is that the x minus 1 factor is squared. So that tells me that at minus 1, instead of going through that x-intercept, it's just going to kiss that x-intercept. And the x plus 2 factor is to the power of 1, so it will go through. Okay, my next step is to find the y-intercepts. So to find y-intercepts, I plug in 0 for x, so I get negative 1 squared times 2, which is just 2. So 0, 2 is my y-intercept. And I'll plot that. So now I want to look at the end behavior. So I use the leading coefficient test. So if I were to multiply this all out, the degree would be 3, which is odd, which means I'm either going to have rising left, falling right, or the opposite. But the leading coefficient is 1, which is positive. So that tells me that it's going to look like this at the ends. And finally, to find the shape, I need to use some more test points. I need to look at some values that are in between each of my intercepts. So maybe I'll look at f of negative 3. Then I'll look between these two. So maybe I'll look at f of negative 1. And we'll look at one beyond here, so we'll look at f of 2 as well. So f of negative 3 is going to be negative 3 minus 1 squared times negative 3 plus 2. And that will give me 16 times minus 1, which is negative 16. So negative 16 is going to be way down here somewhere. This is the point, negative 3 comma negative 16. F of negative 1 is negative 1 minus 1 squared times negative 1 plus 2, which will give me negative 1 minus 1 is negative 2, squared is 4. This is times 1, so 4 times 1 is 4. So at negative 1, I'm up at 4. F of 2 is going to be 2 minus 1 squared times 2 plus 2, which will be 1 squared times 4, which is 4 again. So now I can connect up these dots from left to right. The end behavior is as I expected. It just kisses the x-intercept at 1, just like I expected, because there's a squared term for that root, and it goes through at negative 2. We'll try to get through one more example quickly, and if we get stuck, then I'll finish it in another video. So here's our other example. I want to graph x cubed plus x squared minus 2x. So my first step is to find roots. To do that, I'll factor. So I can first pull out an x. I can factor that further into x. Oops, that's just a 2 left. Oh, hold on. I think that I wrote this problem incorrectly. No, we're okay here. So what I need to do now is come up with the 2 factors. These 2 will multiply to x squared. Then I need to multiply to 2 and add to positive 1. So I have plus 2 and minus 1. So then by the factor theorem, my roots are 0, negative 2, and 1. So I'll plot those as x-intercepts. Step 2 is to find the y-intercepts. So I do that by plugging in 0 into my equation. And that's 0. So the y-intercept is just 0, 0. I've already got that one plotted. 3 is end behavior. So I have odd degree, positive leading coefficient, so it's going to look like this. And now I need to do some test points in between. So maybe I'll try f of negative 3, f of negative 1. Oops, that one was wrong. F of a half. So f of negative 3, I can just plug straight into here, so it'll be negative 3 times negative 1 times negative 4, which is negative 12. 1, 2, 3, 4, 5, 6, 7, 8. So negative 12 is going to be way down here. F of negative 1 will give me negative 1 times negative 2, which is just 2. F of a half, this one's a little tricky, will give me a half. 2 plus a half is 5 halves. And then a half minus 1 is minus a half. So this gives me negative 5 over 8, which is just a little bit more than negative a half. And now I can connect up these dots, just like before. And the end behavior is just as I expected. So I hope that these examples give you some good strategies for graphing polynomial functions, and let me know if you have any questions.